Hello, welcome to this third video of the dark matter part of the module. Let me put it up. Here we are exploring now the production of dark matter in the early universe. For this we are exploring how dark matter is created or generated in situations where you are close to thermal equilibrium and there are some extra processes connecting dark matter to other particles. So we are exploring the number of dark matter particles, which we denote by a letter N here, and those that are in a volume element which is expanding as the universe expands, and that means that the volume element behaves as a to the cube, okay, since each of the sides of the volume expands as with a factor a, growth factor. There is a constant which is not important, so kind of a normalization. And what we want to understand is how this number of particles in this volume, okay, unit volume if you want, evolve as the universe expands. If nothing happens, they will just dilute. So that means that the number is constant, so the number per unit volume, okay, grows as like changes as 1 over the volume, right? But if, so this is the number density, but if there are new particles being created or these dark matter particles are annihilated, then this is no longer true. Okay, so there will be some changes. How are these computed? Well, for the loss of particles, you want to now, in the particular process you are exploring, which are the probabilities of dark matter 1 and 2, for instance, annihilating into other particles. So you need a quantum field theory calculation where you compute the matrix element and the square of it, the probability. You want also to know how many particles are in state 1 and state 2, all right? And you also, and this number of particles in state 1 and state 2 is going to be given by the PDF, the probability distribution, which tells you, remember, number of particles in a range of momentum. So here we don't care about position, so the position is fixed if you want. So we want to know how many particles of a particular momentum are there. And this is given by these distribution functions, F1 and F2. And finally, you need some extra factors that are not going to be important, having to do with the fact that you decay into fermions, you have Pauli blocking, so it's hard to or impossible to decay into already occupied states. And if you decay into bosons, you have boson enhancement, so you enhance the decay rates. Okay, this thing. And finally, you have to integrate this over momentum, so all the momentum states in the initial and final states. Okay, so somehow this goes now slower than before, but okay. So these momentum differentials are standard, so it's the differential of each momentum. Here it should be 3. And divided by the energy to normalize them in a Lorentz invariant way. Not important. So this is for the loss of particles, but for the creation of particles, you have to explore the other process. So AB going to 1, 2. And this is given by, again, some probability. And you have to multiply by the number of particles A and B, integrate over momentum. And again, by these extra factors having to do with how often, how the final states are occupied and if they are fermion or bosons. Okay, all this is just the main equation that we have to solve. Solving this equation in general is impossible, so we're going to take some approximate, well, impossible. You can do with computers, but it's very hard. So we need to make some approximations to understand how to do it analytically. Okay, so let's do it little by little. The first approximation we take is that the rates of going from 1 to 2 to AB are the same as AB to 1, 2. So this is basically true in a CP invariant theory. Then the second is that we are at low temperatures as compared to the standard model particles we are creating. That means that the typical occupation number is going to be small, okay, because the temperature is so low that only the low energy states are occupied. So that means that the typical distribution function for equilibrium reduces to this simple form, because t is so small that the prefactor is very big, so it overtakes the plus or minus 1. We also consider that the particles A and B are in equilibrium, and this is because they are standard model particles. Okay, and being standard model particles, they interact very often with each other, which keeps things in equilibrium. Okay, so the distributions of A and B are equilibrium distributions, are low temperature, so given by what I wrote before. And finally, we are going to assume that F1 and F2 are close to equilibrium, so they have been created or annihilated close to equilibrium, and there is a distribution for them which is close to equilibrium plus some extra contribution. Okay, so from here it takes some steps to derive the next equation, which is the transformation of the right hand side of we had here, okay, into a more manageable expression. So I'm not going to go through the steps, but the idea is that eventually everything boils down to the left hand side being the same as before, and the right hand side, being given by a thermal average, if you want, cross section, number of particles per unit volume square, and some equilibrium distribution for the number of particles we are exploring. So that would be for the number of particles in the dark matter, right? So this is very good because you already can see some physics here. For instance, if this is time independent, you want to be close to equilibrium, and if this is time dependent, the equilibrium configuration is going to be achieved at rates depending on whether this factor is big or small. Okay, if this is big, then it should go to 0. So this is, as I said, this is today. This is communicating very slowly. So let me pause a bit and try to fix it. Okay, now it works better. So this is a thermal average cross section. So remember, it has all this integration here. It has some delta function for conservation of energy and momentum, the probability of the events that we want, and this is integrated over the equilibrium configurations. All right, so that's why we call this a thermally average cross section. Okay. Cool. So once we have this, we have to also understand what's going on with the growth factor. So with this A factor here. Now we're back to where we were before. All right. So I was saying that we have to know what was going on with the growth factor here. And remember that the growth factor, once you take the derivative with respect to time, it's normally written in terms of what is called the Hubble function. So this Hubble constant sometimes called, but it's indeed a function of time, which is nothing but the derivative of a with respect to t normalized by a. So it's the rate of growth of the sorry, I'm in a table which trembles with the as the universe expands. So the rate of growth, okay, the growth rate. Right, so we take this derivative on the left-hand side, and you can write it this way. And now it is where you see that if this factor here and this factor here are similar, or one bigger than the other, or one smaller than the other, you have different behaviors of this equation. So let's see what happens if this can be ignored. So if the rate of expansion is very small, in this case, what is going to happen is that n equal to n equilibrium being constant is a solution, right? Because then n being constant solves this you can ignore, and this should be equal to 0. Okay, how do we know when this happens? So we need to know what h is, and h, okay, is given by the Friedman equation that we wrote before. So is the expansion rate of the universe is basically sourced by the energy density in the universe. And what is the energy density in the universe, which is important for us? It has to be the one important at early times. And remember that at early times, it's radiation that dominates, because we remember that we had this picture on the different evolution with time on the energy densities, and radiation is the one that picks up at early times. So if you are at redshifts, remember redshift is telling us how far in the past we are. At high redshift, we are very early in the past, and if this redshift is bigger than 10 to the 3, so the universe was smaller by 10 to the 3 factor than today. In this case, only radiation dominates, and you know that the energy density of radiation is something we computed. Well, I told you what it is. It's given by a number depending on the number of degrees of freedom and then the temperature. So this you can multiply by each degree of freedom, okay, which here is called with a star. Plugging back this into this equation, you find a number, okay, that then you can put back into here. Okay, very good. So as I was telling you before, we are back to this simplified form of the equation governing the number of particles appearing or disappearing in the early universe. And when h is of the order of what? Of this quantity, okay, then these two are comparable. If hn is much bigger than this term, that means that the universe is expanding so fast that you can forget about this term, and the only thing that happens is that n is evolving as simply a diluting gas, and if this term is bigger than this term, then things tend to go into equilibrium, okay, because then you can forget about this and again go back to what we had before. So it's when h is of the order of gamma, where gamma is defined as basically this guy, so there is n here that goes away, so that the phenomenology changes. Unfortunately or fortunately, the cosmologists like to talk about yield instead of number density, and the reason is that the number density evolves with as the universe expands, and the yield doesn't. So in an expanding universe, the yield is constant. Okay, so what is the yield? The yield is defined as the number density divided by the entropy per unit volume, if you want the entropy density. Okay, the reason why this is used is because the entropy is constant if there are no sources of heat or dissipation. So it is a good quantity to define a process which is only evolving because the volume is changing. So entropy per unit volume is little s, and so how do we compute the entropy per unit volume? Well, this requires some manipulations of the standard thermodynamics equation for entropy, and well, in the notes I give you some hints. Eventually you can prove that the entropy per unit volume is given by the energy density plus pressure divided by T. Okay, remember that we know how to compute energy density given a distribution function. For the pressure, remember that the pressure is the force divided by unit area, and this can be computed using also some formulas from statistical mechanics. And if you know the distribution function, the pressure has to do with the average momentum squared divided by the typical energy of each of these particles. Again, if you have not seen this before, I give you, this can be seen in one of the references I give to you. Okay, if not, well, yeah, it's you can take this for granted. I'm not gonna explain it. The good point of using entropy density, as I said, is that it evolves. If there are no heat source of heat or dissipation, it evolves as 1 over a to the cube. Just as the volume dilutes, it simply disappears, but there are no other non-trivial processes for the entropy. So that's great. Once you put together rho and p for relativistic particles, you find the value of this energy density per unit volume, okay, which is given by this number here. So it's 2 pi squared over 45 g star t cube. where G star is 7/2 for fermions and 1 for bosons. Okay? If there are more particles, you have to multiply this by the number of particles in this relativistic collection of particles. When you put the equation that we had before in terms of the yield, the good thing is that we're gonna absorb this term here, okay, and the yield the time dependence on the yield as time evolves is given by simply the derivative of y with respect to t equals to entropy average cross section y squared minus y squared equilibrium. Okay, this is what it is. It takes some algebra to do it. It's not particularly illuminating to go through it, so I let you do it yourselves. Eventually, we can keep simplifying these expressions, and for the case where we want to explore, we are going to explore it at temperatures which are bigger, okay, than the typical mass. Okay, that means that we are at the early universe, smaller than the typical mass. That is what we want. Remember, for these equilibrium configurations we wrote before, right? We are always going to be in low occupation number places. So we're going to explore t much more than m. That means that if we consider the variable m over t, we are in the limit of x much more than 1. Why is this variable important? Is because since the temperature of the universe is always decreasing, okay, well, most of the time, at least in the early universe, we can use t, big T temperature as a time variable, and instead of having the derivative with respect to t, we can have the derivative with respect to temperature. Okay, this is more physical, right? Because the times are always, depending on how do we define things. So once we put all this together, okay, we can go and finalize the change of variables here. Okay, put it in terms of t. Okay, the left hand side is the same, and I have introduced a rate, okay, gamma, and you can verify that in this equation the Hubble function appears, and this rate gamma is what we have defined before, nothing but number density multiplying average cross section. Okay, very good. So we are ready to the final formula. So once this is the same equation again, time dependent on the yield, and if the last bit is simply introducing here the formula for the entropy that we know already, is this formula here, okay, and the formula for the Hubble constant, Hubble function that we know already for the early universe. Okay, here it is, which is going to depend on the number of degrees of freedom in the plasma. Both of them are going to depend on that. And finally, these two functions, okay, simplify into a constant multiplying this equation, which is a constant depending on the number of degrees of freedom, G star. Then it depends on what is called M Planck, and M Planck, what is M Planck? Well, M Planck is 1 over M Planck square 1 over 8 by j. Okay. Well. And finally, there are these J star differences. One of them, remember, comes from the entropy, another one from the degrees of freedom, which are relativistic. So these two numbers can be different. That's why you have to be a bit careful on how to define them. So this is the number of degrees of freedom, which are relativistic, and these ones are the number of degrees of freedom that contribute to the total entropy of the universe. Okay, these two can be different. In principle, everything is relativistic, they coincide. I'm going to skip the comment on kinetic equilibrium. All right, so this is not so relevant for this module. Well, just let me tell you that we have been exploring what is called chemical equilibrium, in which dark matter goes to standard model, but you can also consider reactions of dark matter standard model going to standard model dark matter. Okay, so those are processes that can keep particles in equilibrium, but what is called kinetic equilibrium. So you still redistribute momentum around, and you tend to generate equilibrium distributions, but in this case, since you don't have chemical equilibrium, you tend to generate what is called a chemical potential. And the reason why this is important is because the rate for these reactions is going to be proportional to the number density of standard model particles and dark matter particles, where the rate of this reaction is going to be proportional to the number density of dark matter particles square. So these two can be quite different. Okay, so sometimes you can have kinetic equilibrium, so the distribution is close to thermal, but not chemical equilibrium. So we are not going to explore this in detail, but this is something that is important in some models of dark matter and beyond. So once we have this equation, we want to understand its different regimes. Okay, so how does the typical yield as a function of time or as a function of temperature looks like? All right, where I have this, yeah, in my notes here. So the typical yield as a function of time has this shape. So first, at early times, it is constant because nothing is happening. The universe is just expanding. Things are kept in equilibrium. Okay, so the same rates that keep things in equilibrium for entropy are also valid to keep things in equilibrium for number densities. Okay, at some point, particles start to behave as non-relativistic particles. In this case, the number density disappears faster than 1 over a to the cube. Remember, it disappears with this exponentially fast. Okay, let me go back to it slowly. Here it is. So number density for relativistic particles goes with t to the cube. T, as you expand, grows like 1 over a. So no, it doesn't grow, decreases as 1 over a. So number density and entropy decreases with the same factor in the relativistic case. In the non-relativistic case, so when the mass is smaller than temperature, then remember that number density tends to disappear. Okay, and that means that the yield tends to disappear. So this is when m is order t. So here we are exploring time in units of, in this variable m over t, x. Okay, so when this is order 1, you become non-relativistic. The particle, if it is in equilibrium, tends to disappear, but at some point you leave equilibrium. Okay, when h is of the order of the cross section, so when you expand faster than the rate at which you interact, and from here on, okay, you are no longer in equilibrium, then you can forget about this part, and the yield is again constant. So you see, you have to see this equation dy dx equals 0. And how does this happen, and how much you create or annihilate depends on how fast you reach this condition. It is kind of anti-intuitive that the higher the cross section, okay, the smallest the yield. Okay, because then if you have a higher cross section, you stay in equilibrium for longer. You stay in equilibrium for longer. Okay, then you disappear more. Okay, because you have been following this for a longer time. So you see what I mean. So this is some equation that has been so for so long in equilibrium that has disappeared almost completely. If you lose equilibrium very fast, then your final yield is bigger. So the final number of particles per unit volume is larger. Okay, so this process is called freeze out. Okay? Particles start to be in equilibrium and they freeze at some value of yield which is constant, meaning that the number density just dilutes as 1/8 to the cube. Okay, and this is what I have written basically here. Okay, so from now on, I think I'm gonna go back to writing things to make. So far, all these equations were a bit hard to follow. To write them live. So from now on, I'm gonna just go back to write things live. Okay, maybe not this one. Okay. Yeah, I'm burning here. This is my. I'm very close to the heating. Okay. So yeah, what we want now is to understand what is the final yield for some of these models. We're going to start with the yield of relativistic species. So that means that a particle that has the couple, say for which the couple means that this quantity is order h, so the rate of interaction is of the order h, when the particle was relativistic. So when the particle was relativistic, okay, the number density, again, is what I just showed you before, and the entropy per unit volume is also a quantity we have seen before. So these two numbers are numbers we have seen, and that means that the yield in this case is, well, a constant. Okay, it's a constant. It depends on the degrees of freedom in the dark matter and the degrees of freedom in the plasma, okay, where the entropy is stored. So this is a constant function, and if it is relativistic, you are here. And now, if the coupling happens, okay, you are gonna keep this value and keep it also all the way. So you're not gonna fall back to very low levels of yield. Okay, that's why the yield is also important. That once if you know the yield in the early times, and then it's frozen, then it keeps the same up until today. Yeah, let me take some water. All right, so let's continue. I was telling you that we now have a process, and the process have left equilibrium at a particular time, and there was a particular yield at this moment, and this is encapsulated by the fact that the number of degrees of freedom in the plasma were whatever they were. For instance, you can have a plasma of neutrinos, electrons, positrons, photons, and in this case the number of degrees of freedom is something like a number you can compute for the standard model. Okay. If you leave equilibrium later, you may have already make some of these particles disappear precisely because the yield of these particles goes to zero, and you may only have, for instance, neutrinos, or because they are no longer in equilibrium. Okay, and you may also have photons. Okay, the entropy depends on the number of particles, that you have in this plasma. Very good. Now, once you have these numbers, the next thing to compute is the observable. We already know how to compute the observable, and the observable is going to be omega today, energy density of the dark matter today, divided by this critical energy density that we already used in previous lectures. Energy density of dark matter today is non-relativistic, so it's mass multiplied by number density of dark matter today. Number density of dark matter today is yield today multiply entropy today. Okay, and this is equal to what? It's equal to the yield when this was generated, because remember that the yield keeps constant after leaving equilibrium, so this number up there. the entropy today is stored in photons, all the other particles that were in equilibrium have disappeared, and this entropy is given by the CMB. So you have to take this, this number here, okay, and use only 2 degrees of freedom today, CMB, and finally, well, that's all you need, okay. So eventually, plugging everything in here and taking, the only thing that you need to know is how many degrees of freedom were active when this particle decoupled. If this happened in the early universe and not around few mega electron volt scales, there are around electrons, positrons, neutrinos, and photons. If it happens after MEV, then the electrons and positrons, because of this fact that if temperature is smaller than the mass, the particles with a certain mass disappear, then electrons and positrons disappears. But if they are, if we are talking about yield generated before, in this plasma you have to put again the E plus, E minus, neutrinos, antineutrinos, and photons. Those are the proper degrees of freedom. Putting all them together, we finally get to the final number. This is given by degrees of freedom in the dark matter, multiplying by the mass. Ta-chan. And this is universal. That's kind of amazing that it doesn't depend on cross sections. It just depends on the fact that this particle decoupled at when it was non-relativistic. Finally, you can compare this with observations. Omega 0 h squared is 0.11, okay, more or less, and h, remember, is 0.7, and this already tells you what is the mass of the candidate of the dark matter required to explain all the dark matter today, which is kind of amazing. So, and this, by the way, gives you an impression that, for instance, neutrinos cannot be the dark matter, but particles with a certain mass, depending on the degrees of freedom, with a certain mass, around few hundreds of eV seems to be good candidates. Very good. So this is the first mechanism, but as you see, it's not very flexible. It's only for one particular mass that you can generate the amount of dark matter that you want. In the second process that we're going to explore, so freeze out of non-relativistic particles, we have more flexibility. Okay? So this calculation is way more complicated. So I'm going to just give you some order of magnitude, and you can find more explanations in the notes by David Cerdeño that I will provide also to you. But for the moment, for this crash course, what I'm telling you should be enough. So if m is much bigger than t, much larger, then remember that number densities have this factor, and basically there is no number density at all. So you have only, if m is of the order t, you have only this possibility for the non-relativistic particles, okay, to be produced in considerable amounts. Okay, so let's explore only this possibility. I'm giving you now for again the situation for 2-2 scattering, and the same thing can be done for 3-2 scattering, and is done in the notes, okay? in the problem. Sorry. So let's assume that we want to know the yield at more or less the moment at which you lose equilibrium. Okay. But we also know that we want to have it when m is order t. This means from this equation that, okay, order h is order t squared over m Planck. Remember m Planck, I told you before what it is. If you want units, it's more or less 10 to the 19 GeV. All right, and eventually this is m squared from this expression divided by m Planck. Okay, very good. Now, what else do we know? Well, we know that the rho, the energy density, the energy density is now going to be given by mn, right? Okay, because this is a non-relativistic particle, and this should go as, from what we just derived, m cubed average cross-section m Planck. Nice. How does this evolve from the decoupling time to today? So those are, remember, something we have already seen. The energy density from this moment is energy density of relativistic particles, which simply dilute. Okay, there is no longer generation of production, they just dilute. So it's going to be given by some rho at some time, and then t. So rho at let's say time t is given by rho at time 0, and then this, yeah, this law, right? So it behaves as 1 over a to the cube, and a behaves less as 1 over t. So the energy density as the universe expands as a function of temperature behaves this way. Okay, very good. So let's imagine that we know the temperature and the energy density at freeze out, which is what we know. I just completed it. And then I can evolve it at later times, yes, from this expression I just wrote. Okay, great. What else do we do? The next step is to put some physical values in, and for instance, we know that the energy density of dark matter equals the energy density of the CMB at redshift 3000. Okay, so from 3000 towards today, dark matter dominates, and before 3000, the radiation dominates. All right, so we can now compare rho f t at CMB time, not CMB, at this, what is called recombination time, sorry, matter radiation equality time. So radiation matter equality time, TF of freeze out, should be equal to the CMB energy density, which is basically given by T to the 4 at CMB times, sorry, at, not CMB times, at radiation domination epoch, all right, which is the temperature of the CMB at redshift 3000, all right, and putting all together, okay, if the CMB today had temperature 2.7 Kelvin, at redshift 3000, you have to multiply by 3000, okay, and you have all the numbers in these expressions around. So this comes from here, this is the same as here, and the T at which the coupling happened is given by the mass of the particle. Finally, the cross-section that provides the dark matter that is important today, so that is important, that is corresponding to the dark matter that we see today in the universe, is given by, you can check this expression, and plugging back numbers, you find what is called the WIMP miracle. Okay, so you see that the average cross-section has to do with the Wick scale, okay, up to a small parameter. So it's going to be a rate that can be close to the weak scale, but still perturbative. So there is this alpha here and this scale. What does it mean? It means that if you have rates of this order, okay, corresponding to the rates that kept dark matter in equilibrium in the early universe, the amount of yield that you generate is the one that is corresponding to the observations on dark matter. So this is a very important result of the dark matter phenomenology. Another way to write this is by saying that omega dark matter h square is basically, how do we compute this? Well, remember that omega dark matter is the raw dark matter today. Okay, so and that you can get from, once you know all these expressions here, okay, once you know the cross section and everything, you can plug it in the formula for how the dark matter evolves with time. And what you find is that this is given by 0.1 square. Okay, so very important. Again, this is telling us that you want to explain the the abundance of dark matter today, you need a cross section which is basically a particle which has the mass of around 100 GeV, and there are some small constants around of order 10 to the minus 2, which is also good. Okay, that means that you are not close to any non-perturbative phenomenon. All right. Again, this is what is called the WIMP miracle. All right, so I think I'm a bit early, well, by 7 minutes. I'm sorry if I rush a bit through the equations. I hope that you got the main message. So what I'm gonna do is then profit to get some extra inertia, okay, towards the next topic, which is gonna be the axions in the as a candidate for dark matter. So this, what we did now, was for the WIMPs, and now we're going to explore axions. Well, maybe before, let me tell you that all the things we did now in this last part are exponentially sensitive to the cross section. So even though all this order of magnitude works, it turns out that this WIMP miracle is not so robust, in the sense that you can easily generate the amount of dark matter that you want, but you can also easily lose it. So it is a miracle in the sense that it works, but it's not a miracle in the sense that if you just take a random model in the electroweak scale, it is gonna give you the yield that you want. All right, so let's change gears, and indeed we're gonna change the order, and we're not going to do axions, we're going to do local detection of dark matter. So we're going to continue in the order that we had already planned. We're not going to continue. We are going to continue in the order of the lecture notes. So local dark matter and direct detection. Of WIMPs. Okay, the reason for this is that this topic is more traditional, and it's important that we cover this a bit more slowly in the next lesson and leave the new ideas maybe for the last one. So a very important feature of the WIMP paradigm is that it, as we're going to see, it has the numbers that allow us to detect it in our detectors. So this is kind of another miracle. You want of the wind miracle is the fact that precisely you can detect the cross sections that we have just derived by building a huge detector. Okay, let's see how can we do this. For this, we need to know the number density of dark matter particles on Earth, and also most importantly, we need to know the flux. Okay, number density multiplied by V. We need to know the flux of dark matter on Earth. And we need to know also how does this affect the experimental sensitivities. So how do we know the number density of dark matter on Earth? Well, we have to explore a bit of the galaxy and its dynamics. So we have to explore galactic dynamics. So the Milky Way, which is the galaxy that we care about for these things, Milky Way, has some properties. So it has 10 to the 11 stars. They live in a disk of size 20 kiloparsecs, more or less. The Sun, by the way, is in the outskirts. Sun. The mass typical distribution is in the disk, but there are others. There's a bulge. There are other places where stars live, and there is a dark matter halo surrounding it that extends to 100 kiloparsecs. Okay. And also in the center of the Milky Way, by the way, there's a huge black hole which has mass 10 to the 6 solar masses. So dark matter halo. And the stars, each star typically weighs the same as the Sun, so the total mass in stars is supposed to be basically 10 to the 11 solar masses. Not exactly, but more or less. This is a bulge. Okay. Yeah, let me do it here. So this is the Milky Way as seen, from the disk. There is also a bulge structure, and many other properties that you can derive from the orbits of stars and trying to see to which gravitational potential they correspond. Okay, the disk has some width. You see, all these things are well characterized by astronomers. Now, given this, how much dark matter there is? Okay, it is not clear, but there are models of the halo of our Milky Way that we will explore in the next lesson, and that will allow us to tell us what is the typical number density of dark matter in different places of the galaxy. I can already tell you that with this kinetic picture, the energy density of dark matter in the solar position is around 0.3 GeV per centimeter cube. Okay, and this is, as I said, corresponding to taking the kinetic data of stars around us, plugging together all these different components like the halo, the bulge, the disk, the black hole, and estimating how much dark matter do you need to be in the dark matter halo to account for these dynamics. Okay, I'm gonna make now a small digression to explore the kinetic picture of the Milky Way. In other words, what is the probability distribution of different velocity states in different places of the Milky Way? This is very important because this is what is going to be characterizing the typical momentum So once we know this from kinetics, we know what is the typical number density given a mass, but we also need to know the typical momentum, because remember that we want the flux, so we need to know the velocity and the number density. And this we're going to do it in the next video, so thank you very much. Yes, this is well, as I said, this module has many different physics. The important thing for me is that you grasp the physical concepts. Then there are the nodes where you can explore them, and in the problems you will be able to deepen your understanding on them. So thank you very much.